Welcome again everyone to the CSEC Physics Masters YouTube channel. The topic that we will be looking at today is scalar and vectors, and this is part one of a two-part video. Since this topic is a bit extensive, so we'll have to use two videos in order to cover it. Please remember to like, share and subscribe to this channel, and don't forget to click that notification bell so that you can get these videos as soon as they are updated. All physical quantities can be classified into one of two separate groups called scalar quantities or vector quantities. And the difference between the two is very simple. That is, scalar quantities only have magnitude, which is just another name for size, while vector quantities have both magnitude and direction. Which basically means that unlike scalars, when representing vectors we have to stipulate its direction along with its magnitude. In analyzing table 4, we see that quantities like mass, distance, time, speed, and energy are scalar quantities, while quantities like force, displacement, momentum, velocity, and acceleration are vectors. Adding scalars is very easy, for you add them as though you would add any other number. But when it comes on to the addition of vector quantities, we have to add both the size and the direction. This is where the resultant vector comes into play. And by resultant vector, we mean a single vector that produces the same effect as two or more vectors combined. Whenever two or more vectors act on the same body in the same direction, the resultant vector is equal to the sum of the individual vectors. In this case, you see that 5 newtons and 8 newtons is moving in the same direction. And when we combine those to produce the resultant vector, it will give us 12 newtons. As you can see, the arrows also shows us the direction of the resultant vector. In the same breath, we can also say that whenever two or more vectors act on the same body in the opposite direction, the resultant vector is equal to the difference between the two individual vectors. This resultant will also assume the direction of the larger individual vector. In this case, you can see that the 8 newtons is moving to the left, while the 5 newtons is moving to the right. That will give us a resultant vector of 3 newtons. And that 3 newtons will assume the direction of the larger individual vector. In this case, the 3 newtons is moving in the direction where the 8 newtons was moving. One should also understand that not all vectors will act along the same line or even parallel to each other. Some of them will act at angles. So let us take a look at vectors that act perpendicular to each other. Whenever two vectors act at right angles to each other, the magnitude of the resultant is found using the Pythagoras theorem, and the direction of the resultant is found using trigonometry. In looking at this example question, you can see that the 5 newtons that runs horizontally to the right is perpendicular to the 4 newtons that runs vertically downwards. And in working this question, the first thing you have to do is to use broken lines to complete the rectangle. After which you have to draw the resultant. And it should run from the corner between the two vectors of the rectangle to the opposite corner. And as was stated before, in order to find the magnitude or size of this resultant vector, one has to use the Pythagorean theorem, in which case the equation will become r squared is equal to 5 newtons all squared plus 4 newtons all squared. Moving down, you realize that the r squared is going to be equal to 25 newtons squared plus 16 newtons squared. The next line of the equation shows that the addition of 25 and 16 gives us 41 newtons squared. So in essence, r squared is equal to 41 newtons squared. However, since we want to find r and not r squared, we have to get rid of the square that is above the r. So in essence, we have to square root it. But since anything done to one side of an equation must also be done to the other side, we also have to square root the 41 newtons squared. So the square root will eradicate the square that was above the r, and square root of 41 will ultimately give us 6.4 newtons. This is the magnitude of the resultant. Now, in finding the direction of this resultant vector, we have to represent it as an angle to either the 5 newtons which runs horizontal or the 4 newtons which runs vertical using basic trigonometry. But in this case, let us use the 5 newtons that runs horizontal. We can also use any one of the 3 basic trigonometric identities, whether sine, cosine, or tangent. But in this case, we are going to use tan as the example. Now, tan theta is equal to the opposite side divided by the adjacent side, where theta is a symbol that we will use to represent the angle. Now, when we talk about opposite side, we are talking about the side that is opposite to the angle. And when we talk about adjacent side, we're talking about the side that is beside the angle, because the word adjacent means beside. From the triangle, we can see that the side that is opposite to the angle is the 4 newtons, and the side that is adjacent is the 5 newtons. So the equation becomes tan theta is equal to 4 newtons divided by 5 newtons. So in essence, tan theta is equal to 0.8. And of course, the newton above will cancel the newton below. The next thing to do is to bring the tan to the other side of the equation, in which case it will become tan inverse. So in essence, the equation becomes theta is equal to tan inverse of 0.8. And when you work this out using your calculator, theta will ultimately become 38.7 degrees. In culmination, your resultant vector is equal to 6.4 newtons at 38.7 degrees to the horizontal force. That horizontal force is 5 newtons. With that being said, this completes part 1 of our 2-part video on vectors, which therefore means that you need to look out for part 2. Please remember to like, share, and subscribe. And do not forget to click that notification bell so that you can get these videos as soon as they are posted. Have a nice day.